what I want to do today is actually talk about some basic fundamental ideas lying underneath, wireless technology and digital communications. And these ideas have been around and been very important in my own research. So I thought I'd start by talking about these ideas, and then a bit later I'll talk about how they impact on my research. Okay, so let's start with some fundamental questions. For example, why do we live in the digital age? What has been driving the rapid pace of change? And even the question, what is information? And then after I've talked about that, I'll then talk about the sort of research we're doing here at Macquarie University. Okay, so the digital world. Today we live in a digital world, and we take this for granted. This basically means that this is a world of zeros and ones, right? Bits of information. Okay, and you could ask, why do we live in this world? Well, one of the reasons is obviously the computer, right? We store information in the computer using zeros and ones. And if you stop and think about it a bit more, the way we think about things, logic, truth and false, can be coded into 1 and 0, and computers are just implementations of logic on hardware. So that's why we live in this digital world. But it's not just all zeros and ones. So in fact, digital means any sort of discrete set of information. For example, the Roman alphabet is a discrete set. And what that means is, when we write letters on a piece of paper, we're doing digital communications. Right? So we can see that digital communications is really important. Okay? But in the real world, there are many signals that are not discrete, and they're actually continuous. All right? And in engineering, we call these signals analog signals. So these are signals that vary continuously in time. All right? So for example, using communications examples, an electromagnetic wave transmitted by an antenna is a continuous signal at some frequency. All right? Another example, when we talk to each other, we use voice signals, which is sound, and sound waves are analog signals. What this means is that your ear is actually an analog device. Okay? It's not a digital device. Okay? So clearly analog's important too, and then this raises the question, how can we get by using just zeros and ones? Right? That seems a pretty important question. So before we get on to that, answering that question, let's look at a little bit of history, and it turns out actually the first electrical communications were actually digital. All right? So if we go right back to 1836, when the electrical telegraph was invented, all right, this was used, so this device in the picture would have been used by a telegrapher to tap out, Morse code. So the telegrapher's tapping that button, and basically the telegraphers are trying to send written text, right, over distances. And that's obviously using this Roman alphabet, which is a discrete set, okay, and it's being coded into noughts, dots and dashes, which, in other words, zeros and ones. So this is an example of digital communications. Of course, the electrical signal that is actually sent down the wire is a continuous analog signal. That's always the case. But what's important is what is the message, right? So communications became analog basically when we invented the telephone, and we started to send voice signals. So here's Alexander Graham Bell back in 1892 when he had just invented the telephone. Okay? Here's an example of an old telephone. All right? Clearly we've come a long way today. This is a modern digital telephone. Maybe 100 years ago, that was an early telephone. And you would pick up the speaker and you would talk into it, and there are sound waves, and those sound waves would be converted directly into electrical signals. There are no bits involved, right? And in fact, telephones have been like that until quite recently. What about mobile phones? Okay, I wanted to picture an early mobile phone example. I sort of came up with this, which I quite liked. I'm not really sure that's really got nothing to do with mobile phones, but it looks good. Okay. So let's move on a little bit further and come to this person. Now, does anyone in the room recognise this face? Who is this man? Claude Shannon. Wasn't very hard. Actually, I know Sam would have known that anyway. And also, I had it in the title of my talk, right? So Wasn't too hard even for others to guess. Okay, Claude Shannon. But Claude Shannon was a pioneer of digital communications, an absolute pioneer. In the 1930s, he was working on electrical logic circuits, okay, which were the precursor of the modern computer. All right? In 1948, he wrote an amazing research paper called A Mathematical Theory of Communication. And this really established the theory behind digital communications. It's been described as the Newton's laws of the information age, and I want to talk about a couple of those laws today because they're so important. But it's kind of amazing. If I showed that picture to someone on the street, they would not recognize this person at all. Shannon actually lived at an exciting time. He was at Bell Labs working on this theory in 1948. At the same time, in the same building, the transistor was invented, all right, which was, you know, the precursor to the modern computer. And so Shannon was certainly thinking forward to an era of computers. So therefore, he was very interested in this problem of how to store information in bits. He could see the importance of that. Okay, so that's one of the things this paper does. But it still raises the question, okay, how can we represent the analog world using these zeros and ones? All right? Well, obviously, what we have to do, we've got some analog signal that's varying continuously in time, and somehow we have to code it into sequences of bits, right, so that we can store them on a computer. And Shannon was very interested in this coding problem. All right? So this is actually a whole field of engineering called analog to digital conversion, and I don't really have time in this very short lecture to go into any of the details. Shannon certainly worked on this. I just have time for one picture to just get across the idea of what it means. So in this picture we can see the analog signal, and then we can see that we've sampled time, and each time point we're outputting a sequence of bits. All right? Those bits represent the levels of the signal at that time. All right? So essentially our analog source can be converted. It can be converted into a sequence of bits, or in other words, a digital signal. And that means we can go away and store that signal on a computer, for example. And I won't go into the details about how you can get back the original signal, but you can get back a good approximation to the original signal from those bits. Not perfect, but you can get a good approximation back. Okay, so let's forget about analog signals. Let's just assume we've converted everything into bits, all right? Shannon was interested in going deeper. He wanted to know how to take these symbols and store them very efficiently. If you think about what a computer might have been like in Shannon's day, there was not going to be much memory, right? So you had to be very efficient in how you stored the information. So Shannon wanted a way to compute the rate at which a source is producing information. So let's have a look at an example. Here's a source producing bits of information, okay? Maybe this is the output of the preceding process, right? So we get some bits coming out, all right? And then what we're interested in is how can we store those bits in the most efficient way, okay? So Shannon would have looked at these bits, all right, and he would have said, well, there's redundancy here, right? There's many more ones than there are zeros, for example. Okay? So from his point of view, there's the opportunity to compress this source into a smaller number of bits. Okay? So what he wanted to do was distinguish between those zeros and ones and the actual unit of information. So he wanted to define a unit of information called a bit. All right? And Shannon would tell us that in this sequence, the ones here carry actually less information than a bit, right? Less than a bit of information. Okay? So you can think about that in a way that when you look at a 1 coming out of the source, you're kind of expecting a 1 anyway, so you don't learn much from it. You learn less than a bit of information. The zeros contain more information because they're rarer. All right? So in fact, Shannon gives us a way to actually work out how much information is in each of those symbols. All right? And therefore, he gives us a way where we can compute the average rate that an information source is generating information. So this is a rate in bits per symbol coming out of the source. Okay? So in a sense, he's defining what is information and measuring it. And he can, so given a source, he can tell you how much information is being generated by that source. Okay? Now his objective was to then be able to compress the symbols coming out into a smaller number of bits. All right? And he achieved that. So he shows us how to do that. He shows us how to compress into a minimum number of bits. Okay? I don't have the time here to explain exactly how he does that, but you can probably imagine that it's very much related to the information rate of the source. All right? If you've got a source that has a lot of redundancy in it and is producing information at a slow rate, then you're going to be able to compress it into a smaller number of bits, right, than a source that's producing information at a faster rate. Okay? So in fact, Shannon, given any output sequence from any particular source, Shannon can tell you how few bits you need to store the information in that source so that it could be recovered perfectly at a later time. This turns out to be a fundamental limit that cannot be beaten. Okay? So this is the first of Shannon's laws, and it's a benchmark that engineers have. When they're designing compression algorithms, they can measure how well they're doing. All right? And over the years, we've got better and better at compressing information. And today, we can drastically shrink images, movies, think JPEG, MPEG, and we can compress files on our computer, think zip. All right? And there are other algorithms out there that actually can compress right down to the Shannon limit. All right? So now let's look at the problem of communicating information. All right? Shannon was very much also interested in this problem. So let's go back to his 1948 paper. He's told us how we can store information as bits, and he's shown how we can do it with as few bits as possible. And he then shows us how to send those bits across communication channels. And you can see that it's very good that we can shrink and use as few bits as possible, because then we don't have so many bits to send across the channel, right? Okay. He also wants to do this reliably. Okay. Now the communications in Shannon's time was analog communications, and actually analog communications is not totally reliable. So Shannon was looking forward to a world in which we have computers talking to each other, like the world we have today, and he could see that it's really important to be able to send bits of information reliably. We can't lose any information at all. Right? That's what he wanted. So how does this come about? The problem with analog signals is that channels have noise in them. Right? So just for an example, think of the mobile sending a signal to the base station. All right? The channel is noisy, and the analog signals are distorted by the noise. So if you imagine you're talking to your phone, the signal is sent to the base station tries to recover the signal, but because of the noise, you get a kind of garbled, distorted version of the voice signal. All right? So Shannon's idea was to use bits to make the communication more reliable. Okay? So here's our mobile. It's trying to send some bits to the base station, that sends them across the channel, and then somehow the base station tries to recover those bits. And you can probably see already that bits are more robust. Right? If there's noise in the channel, right, it's going to be harder to flip a bit from a 0 to a 1 or a 1 to a 0, all right? Whereas an analog signal could get distorted. All right? That's certainly true, but that's not good enough for Shannon, all right? Because the noise could still flip the bits, all right? There still could be errors in the channel. Okay? So Shannon wanted communication to be completely reliable. So he looked into this further, and he looked into coding, all right? So in coding, you add redundant bits to the information bits to enable the receiver to recover the information bits correctly. So for example, if I wanted to send those 4 bits, 0, 1, 1, 0, okay, my mobile could add some redundant bits. These are not information bits. These bits actually depend on the information bits, so they're redundant. Okay? But this can help the receiver decode the signal. So for example, you can imagine that if one of these bits was flipped by the channel, right? So this is actually called a code word, right? So for every message, there's a corresponding code word, right? Now if one of these bits is flipped, then the base station sees that it doesn't have a valid code word anymore, all right? So its job is to pick the closest code word, and it picks the closest code word, which would be this one, and so then it gets back the information bits correctly. Okay? So this is the idea of coding. But can anyone see a problem with this? What might be a problem?
You're sending twice as much data.
Yeah, you're sending here. In this case, this is probably not a very good code, but you're right. We're sending now, instead of sending 4 bits, we're sending 8 bits. All right? So that's the problem. Adding extra bits slows down the rate of sending information. Now, probably in Shannon's time, if anyone else had thought about this problem, they would assume that to make the communication more and more reliable, okay, you would have to add more and more redundant bits, okay, and therefore slow the communication right down. But Shannon showed this is not true. All right? Surprisingly, Shannon shows that we can make the channel as reliable as we want without slowing it down, provided, okay, there's a proviso. The proviso is that we don't try and send our information bits too fast. We don't try and send them through the channel too fast. So Shannon actually defined a notion of capacity of a channel. All right? So given a channel, he can compute a capacity in bits per second per hertz. All right? If you try and send your information bits through the channel at a faster rate than that capacity, Shannon shows us that it's impossible. You will fail. Right? You will make lots and lots of errors. All right? But he also shows that if you try and send the information bits through the channel at a rate lower than the capacity, even very close to the capacity, it's possible to do it. And you can do it through error control coding, like we saw before. All right? So just for an example again, let's look at the mobile sending to the base station. All right? So you can compute the capacity of this channel, and it tells you how fast you can send information through the channel. All right? Now, a particular simple version of this channel has a capacity. Now, I'm only going to put down one formula in this talk, okay, but I think I can get away with this one. This is Shannon's famous formula from his 1948 paper. All right? This is the capacity of a channel, like the mobile radio channel. Now, what does it mean? Well, the SNR is a measure of the received signal strength relative to the noise at the base station. Right? So what we do to get the capacity, we add 1 to the SNR, and then we take the logarithm to the base 2. Right? By taking the logarithm to the base 2, we get a measure in bits per second per hertz. Okay, so this is a formula for a particular channel called the additive white Gaussian noise channel. Now this is sort of Shannon's second law, if you like, and this formula has really been a benchmark for engineers trying to design digital communication systems for the last few decades. And gradually we've been able to get better and better until today we can send information basically at the Shannon rate, okay, using very sophisticated error correcting codes. Actually, it took a long time for this to happen. I mean, it's 70 years. At first, Shannon's work didn't make a major impact. And the reason for that is because we needed smart computers. Basically, our mobile phones today are really powerful computers, and they have the computing power to do the coding and decoding required of Shannon's theory. So it took a long time before we got to that point, but we're at that point today, which is why we have digital technology. I should also add that Shannon gave the method to get the capacity of any point-to-point channel, not just that channel. Okay. All right, so where are we today? Okay, does that mean the whole problem's solved? Well, actually, we're in a situation of a wireless data crunch. Okay, so Cisco predicts that over the next 5 years, the amount of mobile data in the world is going to multiply by a factor of 18. All right? Well, why is that? Well, that's largely because these things are now smartphones that can send images and video. And Cisco predicts that by 2016, 2/3 of all data will be video traffic. All right? And the big problem is we've only actually got a very small range of frequencies that we can actually use in mobile radio. Okay, so we've got this data crunch problem. How are we going to do this? All right, so our research here at Macquarie University is directed towards trying to solve this data crunch problem. So what we have to do, we have to go beyond Shannon. All right, we have to start looking at networks. So what I have here is a picture of a cellular radio network. These towers here represent the base station towers, and these are all mobiles, and this hexagon represents a region of coverage of that base station. All right? And such a hexagon is called a cell, and that's why we call it cellular radio. All right. Now, I was looking at my PhD 20 years ago, and I was asking the question: what is the Shannon capacity of this cellular network? All right. At the time, okay, the way cellular networks were designed, there was a big problem of interference. Right? So mobiles in adjacent cells interfere with each other. So what they did is they made sure that mobiles in adjacent cells don't use the same frequencies. All right? So the colours in this diagram represent the different frequency bands allocated to each cell. So a cell might only get a third of the total available frequencies. All right? That's how it used to be done. Right? So I wanted to see if that was efficient, and so I tried to calculate the Shannon capacity. Now, to make it tractable, I looked at a model where all the base stations are connected together, by, so they're essentially cooperating. You could think of this as a big array of antennas. Okay, the base station is just one big array of antennas. Today we would call this a multiple input, multiple output channel, because the multiple mobiles provide the inputs and the multiple antennas at the base stations provide the outputs. All right. So by doing that, I was able to calculate the Shannon capacity, and I was looking at the particular direction the mobile sending to the base station. All right. So what I was able to show is that actually this scheme that they were using at the time only achieved 1/3 of the cellular network capacity at high SNR. Okay. Well, today we do use the full bandwidth in each cell, so we don't do that dividing up into 3 anymore. All right. And actually today, this model of connecting all the base stations up is actually becoming of interest to real engineers. Okay, so standards are being developed at the moment for the systems that have these base stations connected together and cooperating. All right. So right now, I'm back interested in this, and I'm looking at the other direction, the base stations sending to the mobiles. Okay, this turns out to be a bit more challenging. We're working on this problem at the moment. About 17 years ago, something kind of similar was done, but maybe a bit more exciting actually, by some researchers at Bell Labs. What they did is they put lots of antennas on a single base station, all right? And they even put antennas on the receiving device, say a laptop, all right? So in this case, so let's say there's n antennas on this base station and n antennas on this receiver, where in this picture n equals 4, right? They looked at the Shannon capacity of that point-to-point channel, and they showed that it had the form log SNR multiplied by n. Okay? So for example, in this particular example with 4 antennas, the capacity is 4 log SNR. Now if you remember before, when you did the single Shannon's formula had a log SNR. But now we've got a 4 in front of it. We've multiplied the capacity by 4. And we haven't even increased the range of frequencies at all. So in fact, by increasing the number of antennas, we can just scale up the capacity. This thing's called MIMO, multiple input, multiple output, and this is going to be very important in solving the data crunch. Right? Now, what do you do if you can't put lots of antennas on your mobiles? So suppose there's only one antenna on each mobile. Well, still you can have MIMO, put lots of antennas on the base station, and just have lots of mobiles. Okay, that's still MIMO. With n antennas at the base station, that base station can send up to n non-interfering beams. It's called beamforming. And this just increases the capacity of the system. Okay. So what I'm doing at the moment, I'm looking at the problem in the context of the cellular system. All right? So we've got all these base stations trying to do beamforming, but there's interference between the cells. So, but let's use this backhaul network that's connecting all the base stations up to coordinate the beams, so that we can sort of aim the beams so that they're not causing interference at the mobiles in the adjacent cells. All right? So coordinated beamforming is something that we're working on here at Macquarie University. And now I'm going to come lastly to probably the most important way we're going to meet the data crunch, and that is small cells. All right? So here is a big base station tower, right? But we can also put little base stations on lampposts, on bus stations, on the outside of buildings. We can even put them inside buildings. All right? And what does this do? Well, here's a picture of the big cells, the macro cells, and now we've put all these little pico cells inside the macro cells. Now, because they're small, the mobiles can use much less transmit power, right? And so if we use a particular frequency in this cell, we can also reuse the same frequency in this cell and in this cell. So we can massively increase the spatial reuse. All right? We can also try and put these picocells where the traffic is, right, where the hotspots are. Okay? So you can see that there's lots of research challenges in this area, and we're working on these at Macquarie University. For example, modelling and design, working out where to put the picocells, where is the traffic. Okay, we have to worry about interference. For example, a mobile that's connected to a picocell, okay, is only using a small amount of power, but a mobile out here that's sending to the faraway macrocell tower might be using a large amount of power and therefore causing a lot of interference at the picocell. So there's an interference avoidance problem and a power control problem, all right? There's also a cell association problem, right? So a mobile now might not connect to the macrocell tower. It's got a choice. It could connect to the macrocell tower, or it could connect to one of these little picocells. Maybe it has a choice of a bunch of picocells. So there's a lot of optimization to do. And of course, there's base station coordination that I was talking about earlier. So these are all of the sort of things that we're going to do to try and meet this data crunch, basically. So in conclusion, we do live in a digital age. Thanks to Shannon, we have fundamental limits on what is possible, and these limits are still guiding us today in research and development. And I also want to point out that there is a wireless data crunch happening right now, and to solve this problem we need new models and new techniques that I've discussed. Small cells will be critically important, so you're going to see small cells coming near you. And finally, I just want to say it's an exciting time to be in wireless research. Okay, many thanks.